Okay, so here we go. We've got these three graphs. The top graph is position, it's horizontal position along a number line. Imagine there's a number line at the front of the room here. We're going to call the kind of left side of the board position 0, and anything going to the right of that is going to be a positive number of getting to the right of the origin. If you forget that, think about your coordinate axis. On an x-axis, to the right is positive, and to the left of the origin, of course, is negative. And eventually we'll add a second dimension to this where things are moving both up and down at the same time, that they're moving left and right, and up will be positive and down will be negative. So the middle axis represents our velocity function, and the lower axis represents acceleration. We've got a number line here at the front of the room, and for the first 4 seconds, so this line links 4 seconds on all three of the graphs. For the first 4 seconds, we're going to say that I'm just putzing to your right at a constant speed. I snap my fingers and I'm moving to the right at 1 meter per second for the entire 4 seconds. So the event begins when I snap my fingers, I move like a robot to your right at a constant speed, and then at 4 seconds I reach this point here. Where am I right now? How far away am I from where I started from if I was moving at 1 meter per second for 4 seconds? I'm 4 meters away. Most of you can intuit that, and if you can't, maybe you're thinking, okay, well, I remember this formula from like an algebra class, kind of a rate formula. Speed is distance over time. The physics version of this, by the way, velocity formally is my displacement, my change in position over my time interval. So this is kind of like the physics version of that. And so if I was moving at 1 meter per second for 4 seconds, I can solve for my displacement delta x by multiplying both sides by the denominator. 4 seconds, 4 times 1 is 4. I'm at position 4 meters. Another way of thinking about it is if I'm moving 1 meter per second, that means at time 0 I'm at 0, and 1 second later I'm at 1 meter, and so on. Okay, so I'm going to start here at the origin at position 0, and I'm going to end here at position 4. Where am I at 1 second? Yeah, I'm at 1, and so I can kind of see here, and at 2 seconds I'm at 2, and I'm at 3 seconds I'm at 3. And what is this starting to look like? Is this a line or a curve? Yeah, it's a linear function. And so as long as I'm moving at a constant speed, if my velocity is not changing at all, then the position graph is linear over that interval. And so I went from position 0 to position 4, and I had this linear function. Now, here's where today's class gets interesting. If I could boil down today's class to a total of 5 minutes, this next 1 minute would be one of those 5 minutes. If I wanted to figure out what the slope of that line was, hopefully most of you would say, okay, I remember slope in math class. We use the letter m, right? Y equals mx plus b in the slope-intercept kind of general form, and it's going to be the rise over the run. Now I want you to look at this graph here. I don't want you to pay attention to the numbers. Clearly the rise is 4. I started at 0 and I ended at 4. What variables are the rise? I don't want you to pay attention to the numbers. I want you to pay attention to like what letters I should be using. Yeah, this is distance. This is distance, or more formally in physics, I could say it's my final position 4 minus my initial position of 0. This is the rise. And so I'm going to write that out, and I'm going to write it out in green. I'm going to say, well, what we really just found was our displacement. Delta x, our change in position, our final minus our initial position. How about the run? What values here are we finding when we find the run in this particular case? I'll let you guys think about that for a second. Yeah, it's exactly what it is. It's time. The run is 4 seconds in this case. So one way I could think about it is delta t. This should look familiar to you. Delta x over delta t, because we just defined it. It tells us what our velocity is. So one of the huge ideas from today's class is that the slope of our position graph is our velocity graph. The slope of that line is velocity. So to get from one graph to the other graph, to go from kind of the upper graph to the middle graph this way, we have to find the slope. Now, is the slope of this linear function the same over the 4 seconds, or does it change? Yeah, it's the same. It doesn't matter whether I test those two numbers, or those two are the total, beginning and end. You guys figure out the slope of the line. I'm going to give you 10 seconds. Figure out the rise over the run. Sydney, what'd you get for the slope in this case? Yeah, 1. The rise is 4, the run is 4, so wherever I was going at any point in an interval, my velocity was 1 meter per second. So the graph should reflect that. That means that I should mark up 1 here. Now I'm going to use open circles. We're going to kind of discuss this a little bit later, why I'm using open circles at the beginning and end of the line segments. But for the whole interval, the velocity of the object that was moving was just 1 meter per second. What if I asked you to find the slope again of that velocity function? First of all, what's the slope of a horizontal line? Yeah, it's 0, right? And the reason is the change in the rise is 0. It started at 1 and it ended at 1. It didn't change, so there's no slope, right? The numerator is 0. So I'm going to do this one time. I'm going to actually write this out. The slope is the rise over the run, and we can say that the values were the change in velocity in this case. That's what the rise is, and the run is the change in time. What variable in this introductory salvo of physics is represented by the change in velocity over the time interval? Yeah, that's what acceleration is. It tells you how much faster or slower you're getting. It tells you how your velocity is changing. We call that acceleration. So I'm going to box this in, and I'm going to say, okay, if the slope of position is velocity, then the slope of velocity is acceleration. So to go downwards on these graphs, you're finding slopes. And this slope over the entire interval is 0. The object was not accelerated. When we look back at the event, click start, I'm not accelerated right now. I'm going at the same rate the whole time until the event ends. So I wasn't getting any faster or slower, and we can say that the acceleration is 0. By the way, that's where these funky units of meters per second squared comes from. Because my change in velocity, if I'm only looking at units, my change in velocity is meters per second, that's in the numerator, and the denominator is seconds. So I have a complex fraction. I can write that as seconds over 1 in the denominator. I multiply by the reciprocal, right? 1 over s to deal with a complex fraction, and I get a meter over a second times a second, or a second squared. Most people are like, what the heck is a second square or a square second? I don't know what that is. A better way of saying acceleration units is meters per second per second. You guys with me on that? Okay. Next 4 seconds, from 4 to 8 seconds. So I'm over here now. This is position 4 meters. For the next 4 seconds, I start and I don't even move. I just park here for the entire 4 seconds. And the next snap is 8 seconds. I want you guys to graph position, velocity, and acceleration for that physical event of the next 4 seconds, from 4 to 8 seconds. I'd like you to do it by yourself for 20 seconds, and when the buzzer goes off, turn to the person sitting next to you and see if you have the same stuff on your graphs as they do. All right, check in with people sitting around you and see how you did. All right, let's check in. Mia, let's start with you. What did the position graph look like from 4 seconds to 8 seconds? By the way, this next vertical line should be 8 seconds.
The horizontal line.
Horizontal line from here to here like that. Okay, that's what Mia said. I'm going to throw this line in here like this. I'm going to call this choice B and that choice A. Michael, which one of those two do you like better, A or B? What's wrong with B?
You'd be going back to where you started.
That means we snap our fingers, I disappear from here, suddenly reappear back at the origin. That's not what happened, right? So that's not right. We stick around right there at 4 meters. Any questions on the position graph from 4 to 8 seconds? Neha, how about the velocity graph? What happens to that one? Hey, one of the cool things about physics is that at the end of the day, it's a very tangible science. And so you can ask yourself, if we start again at 4 seconds, how fast am I going right now? I'm not, right? 0. There's almost like, there are times when physics will feel really cerebral, where you're like, I gotta do the math. And then there's gonna be times where you need to like take a deep breath, back up and be like, dude, what's it, like what does it look like? It's not moving in this case. And so you can use your advantages here of having lived in the physical world to kind of help you with some of these problems. So it drops immediately down to 0. There's an open circle here, and what that technically means is we're not defining the velocity at that transition point, because if I'm going from 4 meter per second to stopping instantaneously, we're ignoring that little transition, and that's why it's an open circle. We'll learn more about that later, but for now we're ignoring it. How about the acceleration graph, Ian? What does that look like from 4 to 8 seconds? You're Ian, right?
Oh yeah.
Yeah, sorry.
It's good. I don't know. I don't know.
Okay, so remember that we have to, if we want to move downward on these graphs, we have to find slopes. So acceleration tells us how much our velocity is changing. That's really what it is. It's a number that says your velocity is changing by this much. Here's another way of saying it. I'm going to show you physically what an acceleration of 1 meter per second looks like. So I'm starting at rest. 1 second later, I'm at 1 meter per second. 2 seconds later, I'm at 2 meters per second. 3 seconds later, I'm at 3 meters per second. Every second, I add 1 meter per second. You with me? It's weird. I'm telling you, you're like, yeah, I got it, acceleration, I'm good. I'm telling you, acceleration is going to kick some behind. Like first year physics students, this is for the first like 3 weeks, maybe even longer, really understanding acceleration is one of the biggest challenges that you guys have. So how much is my velocity changing during this time? It's not. It started at 0 and then ended at 0. Here's another way of looking at it. It's if you don't have a good intuition for acceleration, you can say, dude, what's the slope of that line? The slope of that line is 0 because it's horizontal. End of discussion, full stop. You can always kind of defer to that approach as well. So we can say then that the acceleration graph over that next interval is 0. We were not accelerating. Are there questions on any of these pieces for the first or the second time interval? Okay, let's try this again. Okay, now I'm starting over here. We're going to call that position 4. I snap my fingers, and for the next 4 seconds, I'm moving at a constant rate to your left. I snap my fingers again, and I'm done at position 2. So let me say that again. I started at position 4. I end at position 2, and I'm putzing along at a constant rate. I'm going to give you guys 60 seconds. You can start by talking with each other. When the buzzer goes off, have all 3 of those graphs filled in for that event. Ready, go.
So that would explain why he's doing this 2 meters in that
All right, Constantine, let's start with you. We're going to start with the position graph. I start at 4 and I end at position 2. Can I connect those 2 points with a line or a curve, Constantine? Yeah, straight line. Hannah, if I just asked you, is the slope of that line positive or negative, what would you say?
Negative.
Yeah, the slope is negative. Alex, do you agree or disagree that the slope is negative?
I agree.
Yeah, what is the slope, Alex, of that line?
A negative 0.5.
Excellent. Negative 0.5 or 1/2, both of those are correct. So this is a negative slope. So one of the things you guys have to say is, all right, I can find the slope of the line. I know that's negative. What does that negative sign mean to us when we bring it down here to our velocity graph? What does a negative velocity mean? I'm still learning names, Aiden.
It's going the opposite way.
It's going the opposite way. And if we call positive to the right, then negative means to the left. And that's consistent with the physical event. The negative sign indicates direction. You are required for a vector quantity to assign a direction. For the beginning of physics, plus and minus signs will be enough because we're moving in 1 dimension. But pretty soon we're going to be moving in 2 dimensions, and then you'll have to use angles. If I have a soccer ball on the ground in front of me and I launch it and I try to hit crossbar because I'm just testing my accuracy on my strikes, the ball leaves the ground at some angle between 0 and 90 degrees. You can't use a plus or a minus sign because there are 90 integer increments between horizontal and straight up. And so I can't use a binary system like plus and minus. So it's negative 1/2. I'm going to start here by identifying negative 1/2 on my graph. And I'm basically going to draw that line in. What's the slope of this line that's going to help me with the acceleration graph? You're Paul, right? Yeah, thanks, Paul. Yeah, still 0, right? This thing is flat the whole time. This is a horizontal line. It's not changing. Are there questions about what we did here? Okay. Remember when I said there was like 5 minutes of stuff? We're probably that we could boil the class down to. Here's the next couple of minutes of stuff you got to really pay attention to. What if I asked you to figure out what the area was bounded by that triangle? What if I started by saying, hey, in that red shaded region, what's the area of the triangle? Hopefully you could find it. I'm going to give you 10 seconds to kind of mentally figure out what the area of that triangle is. Sammy, what do you got for me?
8.
8, right? 1/2 the base times the height. What if I said, what's the area of this rectangle right here? What's the area of that one? Yeah, that's 4, right? So I'm going to write this one in, and I'm going to actually put a positive sign here. It turns out that when I asked you to find the area, you multiplied the base times the height. And what you actually did is you multiplied time times velocity when you did that. And it turns out that time times velocity tells you how far you went. Right? So if I algebraically solve this for delta x by multiplying both sides by delta t, right? The delta t here cancels the delta t here, and I get delta t times my velocity will tell me my displacement. It'll tell you how far you are after the interval from where you started from. So if I started at 0, I end plus 4 units away. So when I'm going upwards on these graphs, I have to find areas. I can do the same thing over this next interval. What's the area of that region? Well, it's 0, right? There was no displacement. What's the area of that rectangle right there? Yeah, -2. Now, I know it's weird to assign a negative sign to an area, but we're actually finding displacements. So how far I am I at the end of the interval from where I started? I'm -2 units. Well, I started at 4, so I end at +2. So whenever you're going upwards on these graphs, you're finding areas. And when you're going downwards on the graphs, you're finding slopes. Okay, last interval. This is 12 seconds. We're going to go from 12 to 16 seconds. I start at 2 meters, and for the next 4 seconds, I get faster and faster and faster. The event looks like this. I start getting faster, 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 and I end over here at the highest speed that I'm going, and I'm 10 meters from the origin. So I start at 2, and I end at 10. I want you to spend 60 seconds filling in the position, velocity, and acceleration graphs to the best of your abilities in groups. Talk to the people sitting around you and see if we can figure it out. Owen, I started at 2 and ended at 10. Should I connect those 2 points with a line or a curve? A line. If I connect those 2 points with a line, that means that the slope at the beginning section of the line is the same as the end of the line. Good, because we know that we were getting faster. This is no longer going to be constant. So now I want you guys to figure out, I'm going to give you another 30 seconds. Is it going to be the dashed curve, which I'm going to say is concave up, and I'm going to call it curve A, or is it going to be this solid curve, which is concave down, I'm going to label curve B. I'm going to give you 60 seconds to discuss this in groups. Pick one of those two, go.
It's accelerating.
All right, Michael, do you like A or B? Mason, agree or disagree, A? In mathematics, the word tangent means the line that just touches a curved surface like a circle. I've drawn a circle over here. There's only one tangent line that I can draw that touches it at one point. There's plenty of lines I could draw, but the lines will either intersect the circle at 2 points or 0 points. But there's only one line that touches it just one time, and it's tangent to the circle. That's the word tangent. If I drew another point, let's call that point 2, the tangent line would look like this. It would have a different slope. In mathematics, the slope of the tangent line on a curve is called the derivative. And it is the fundamental idea to learning calculus. So, you were not learning calculus in this class, but we're going to use the idea of a derivative. Let's take a look at curve A, point 1. The slope of the tangent line is nearly 0. It's slightly positive. And we know that the slope of this tells me what my velocity is doing. Curve A, eventually up here at point 2, gets very, very steep and positive. That means that my velocity started small and positive and ended much larger and positive. Is that what happened? Yeah, that's what happened. Curve B, on the other hand, starts very steep and approaches 0. Is that what happened? That's not what happened, and it's not curve B. I'm going to recommend that you use the slope of the tangent line analysis to figure out which way it's curved. This is a very difficult thing to do for first-year physics students, figuring out which way it's curved. Let's take a look at the line that I drew here for the velocity graph. It now has a slope. What's the area under that velocity graph? 8. 1/2 the base times the 8. That tells me how far I went. I went from 2 to 10. It tells me my change in position. How am I going to get my acceleration graph? Is it going to be 0 or not 0? Not 0. Now, this thing has a slope. And when I go in the downward direction, I have to figure out what the slope is. I'd like you guys to finish by drawing in the acceleration graph. I'll give you 1 minute. Okay. 10 more seconds.